This is the brief on the fundamental continuity equation in convective flow.
So what does that mean?
Well, this is the mathematical framework that lets us track how the concentration of a material changes, whether it's sand grains dispersing in the air or particles in a chemical reaction. It's all about movement and internal processes. First, let's cover the baseline scenario. You have convective flow with no internal sources or sinks. Think about material that's just moving around, like grains of sand thrown into the air. No new grains are being produced, right? In a case like that, the equation is just a simple balance between the rate of concentration change and the movement of the material across boundaries. Second, what happens when you introduce an internal destruction process, or what's called a sink term? Well, now the concentration of particles decreases much faster. And that makes sense, because the sink term is working in tandem with the flow to clear the material out. And that brings us to the final crucial point. For any accurate real-world modeling, you have to account for both things. Any change in local concentration has to mathematically balance two elements: the movement of material across its boundaries and the rate at which that material is being created or destroyed inside the volume itself. The essential distinction in the continuity equation, then, is between simple material movement and movement that's coupled with internal production or decay.